Okay. You're first. Congratulations. Let's see. Let's do something like this to start. Good morning. While I pull up Twitch over here. Cool. Actually, I guess I have to pull up Google, because I need to do some math. Let's just start off today with another Sig Fig problem. We'll do this lovely math here, and then we'll worry about dealing with units. All right, let me just do some simple math here, then we'll talk about the Sig Figs. All right. So, we have a couple of numbers here that we're going to be dealing with. And we're doing, looks like, a mix of various operations here. We're doing addition and subtraction, and then we're going to be doing division afterwards. Right, so that's what the parentheses are there for. So I've done the addition and subtraction for us, at least numerically speaking. But I have not done the sig figs for this yet. And if I were to do this next part, by the way, I would get 4.97125, whatever. That's enough for us. Morning. So if we look at our first kind of sum up there, we said that was 24.21. If we recall our rules, we want to kind of figure out where the significance ends in those numbers. And so we're going to see that we're technically only going to have this number to be significant to that tenths place. So technically, that is our last significant digit in the number. Though again, we're not going to round until the very end. With the next one, 4.91, oops. 0.04. Looks like both of these will have the same spot. So in fact, everything will be significant there. Lucky us. So we don't even have to, well, I mean, we'll just put it anyway. And maybe we won't. If we're comparing these numbers, now that we're dealing with division, now that we figure out the sig figs for addition and subtraction, we have to now apply our rules for multiplication division, because that's our next operation. This number on the top has 3 sig figs. Remember that 1 does not count for our sig figs, because that was technically something we would have rounded if we were done. Number on the bottom also has 3 sig figs, inadvertently I suppose, which tells us that our answer should also have 3 sig figs. So we're going to want to round based on this 1 here. And since that is a 1, we're just going to round our answer to 4.97. And we're done. Hooray! So hopefully this is a little bit less daunting than it was yesterday. Maybe it's gotten some time to kind of settle in a bit, which is good, I hope. And I hope taking a look at the homework too, that'll give you more practice with that. Are there any questions with this particular problem or any of the ones we did yesterday? be happy to go over those before we go into units. Or we can just go ahead, which is fine with me. As always, you guys can always throw things. What are the bottom portion of different sig figs? Yeah, let's pretend here. Okay, so 24.21 over. Now let's pretend it's here. Let's pretend it's that now. So if this one were 3 sig figs and this one were 4 sig figs, of course we would choose okay, well yeah, so I mean we could really completely just destroy this problem. Yeah, let's do it. Okay, fine. All right, so let's say instead of that thing, let's say we had our 24.21, same thing as before with its 3 sig figs. Let's say instead we had 4.91 minus 4 on the bottom. No, there's nothing to be sorry about. This will be an interesting exercise here. So if we had 4.91 and 4 that we're subtracting, now the decimals aren't lining up. Well, I mean, they line up, but I think this is what you meant. Oh dear, this is actually going to be a problem. No, it's not. I mean, it's kind of a problem. We technically have a 0 in our sig figs. We have 0 sig figs, but I don't want to say our leading 0 is significant there because they shouldn't be. But this number will have 1 sig fig. Let's just leave it at that, perhaps. Kind of a disaster of a problem there. If we were to do this, and somehow we have 1 sig fig and 3 sig figs, doing the math, let's see what we get. 24.21 divided by 0.91. We get 26.604, whatever. If we look at the sig figs and somehow this number had 1 sig fig, I guess we'll say, versus 3 sig figs, we would have to choose 1 sig fig. So we would have to keep that 2. We would have to round based on the 6, which would give us the answer of 30. If that was what we had there. So in that case, that would, with multiplication division, you'll always choose the smallest number of sig figs. So if our first top number numerator had 3 sig figs, our denominator had 1 sig fig, we would choose 1 sig fig. So we'll round our answer to 30. Or if we wanted, we could say 3 times 10 to the first power. Either way would work. So, fun stuff there. Cool. Alrighty. In that case, let's talk a little bit about units, and then we'll talk about conversions and that sort of thing. So, I'm sure you've been drilled in, like 3rd grade or whatever. You've probably all seen that meme where it's like the math teacher says, or you say to the math teacher, the answer is 30, and they say 30 what? 30 bananas, 30, buckets of paint, whatever, Units are important, right? So I'll put that meme in for you guys later, perhaps. It's an older one, but we'll allow it. Units are kind of an important part because in science, numbers don't just stand alone necessarily. We're going to see that, in order for a number to express something about matter, whether that's a temperature or a volume or a mass, we have units to kind of help us categorize what type of measurement we're talking about. And it will also kind of tell us how big that measurement is going to be. So, let's start with some mass units here. Mass, of course, is kind of related to the amount of substance. For us, because all the chemistry we're going to be doing will be on Earth, that's going to be the same thing as weight for us. I'm going to put that in parentheses. Okay, I don't want to make this seem like an equation there. Technically, weight is a force. Physics people will get very mad if I tell you that mass and weight are the same. But all the balances and scales that we use to measure weight do so using force anyway, so kind of a moot point. And since we are on Earth, they will be the same anyway. So we'll be okay with that. But technically, weight is not the same thing as mass. So, some units of mass. For the metric system, we have the gram, or more accurately, technically, the official unit is the kilogram. But gram would be the base unit there. For the US system, we have pound, which is abbreviated LB for some reason, which is especially odd considering that neither L nor B are in the word pound. But go figure. We're going to see I pretty much am anti the US system or UK system. It's just bizarre. Anyways, those are kind of the main libras. Okay, yeah, for the scale they use to measure the pound. Oh, interesting. Okay, makes sense. Good to know. So yeah, go figure. So it's from a measurement device that they used to measure out pounds. So those are kind of our main units there. You may have other ones. In the U.S., you have grains, stones. Well, I guess these are more in the U.K. These are all components. I think there's 14 pounds in a stone, and how many grains in a pound? I don't remember. You also have ounces. Ounces, there are 16 of those for a pound. That's the thing that sucks about the US system is there's all these just kind of arbitrary numbers of how many of whatever there are. You have tons as well, which are 2,000 pounds. It's kind of just all over the place. Whereas with the metric system, we pretty much only use the gram. And we're going to throw prefixes on that. We have kilograms, we have megagrams, we have micrograms, but they're all based on that unit of grams. So just putting some units out here. Yes, indeed. Evil U.S. system is ruined. It's interesting because the U.S. is kind of like halfway. We're stuck halfway in switching to the metric system. That's why, like, if you go and, take your can of Pepsi or whatever, it has both units on it. I don't know how focused this is. It has, if you can see there, it says 12 fluid ounces and 355 milliliters. It has both units on it. And so if you go to the supermarket, you're looking at any of your things, if you're looking at a bag of Cheetos or whatever, it's going to say both a US weight unit and metric weight unit. Same for liquids, you'll see volumes in both units. It's just kind of bizarre. We're stuck halfway through. This was back in Jimmy Carter's day. He was trying to get the U.S. to go to the metric system, but when Reagan came in, he put a stop to that, and so we're kind of stuck in limbo here. So that's why some things are given in one unit explicitly, like gasoline is done in gallons, but car engines are done in liters. It's just bizarre. We're kind of just in this nowhere of being stuck with both systems. So go figure. But that's a tangent. I like tangents. Alrighty. That's mass. Good enough. So volume is going to be how much space something takes up in 3 dimensions. We have some volume units here. For us, we have a couple of metric units. We have the liter and the cubic meter, and this is how they are equal to each other. 1,000 liters is 1 cubic meter. So a cubic meter would be the volume contained by a cube that is 1 meter in each direction. So a meter is 3.3 feet, so a little bit, for me that's probably my arm span, something like that. So imagine a cube make of that. That would be 1,000 liters there. We would have also various derivations of these. We could have cubic centimeters, which are sometimes called cc's. Like you'd, if you have the old time, medical dramas on, they say, we need 20 cc's of blah stat. They're talking about cubic centimeters. For us, not for us, actually. 1 milliliter is the same thing as a cubic centimeter that we're going to learn later on. We'll learn about these prefixes. But typically for volumes in the metric system, we talk about them in either cubic meters or liters or some derivation thereof. Again. In the US system, of course, we have 1,000 other things. We've got gallons. We have quarts. We've got pints. Cups, fluid ounces, what else do we have? Teaspoons, tablespoons, all these horrible random units that we're probably more familiar with cooking than anything else. Because we often use volumetric measurements there. So those are kind of units you might be associating with volume for that sort of thing. All right, let's see. What else do we have? Oops. For length, I hopefully don't need to describe length to you or define it. The SI unit, or not SI, well, yes, SI, but metric unit, we'll say, is the meter. You can, of course, put other prefixes on that. We can get kilometers, we can get micrometers, nanometers, all sorts of fun things. But for US, of course, we have miles, yards, feet, inches. What's below an inch? I don't know. Farthings. I don't know. We've got all these random units. Leagues, I guess, is another one. That's another length unit in the US system. The last two are probably more British than anything else, I would think. Or they're more kind of used for kind of like naval systems, I want to say. But yeah, these are kind of like medieval units, so they're not really used very often anymore. We typically just cap out at miles in the US. Let's see, what other units do we have? How about energy? For metric, we actually use the same units, thankfully, for energy. We have joules, which is sorry, the actual unit is not capitalized, even though it's some guy's name. Capital J is what that unit is. And then we also have the calorie, which is abbreviated cal. So if you, for example, take a look at your nutrition label on the back of your whatever, you're going to see things, you're going to see a lot of these units. You're going to see calories, for example, if you're in the US, you're going to see milligrams and grams when you're looking at the protein and the, sodium and all that stuff. You're going to see potentially a volume on there if it's a liquid. If you're in Europe, though, you'll probably see kilojoules instead if you're looking at the energy content of whatever your nutrition label is. So these units are used not interchangeably, but they're used in both systems. So yes, and we're going to see they're actually both they're both used in chemistry as well. Let's see, what other units do we have? What have we not talked about? Oh, temperature. So you might be familiar with temperature as how hot something is. Right now in Ridgecrest, it is, in my opinion, freezing. But we can kind of understand the temperature is low outside, so I keep the temperature warm inside. But technically, that is the average kinetic energy. Temperature is very related to the rate at which things are moving. So technically, our temperature is not how hot or cold something is. That's not really a scale we have. It's more of a relative thing. But in chemistry, we kind of have temperature being proportional to kinetic energy. So that is your fancy definition there. We use two different units in chemistry. We can use Celsius or Kelvin. Those are the typical ones we would use. Of course, in the US, we have the Fahrenheit scale. I will not be throwing Fahrenheit at you at all. So, you've probably learned that formula way back when, 9/5 times degrees Celsius plus 32 to get to Fahrenheit. Who cares? Don't worry about that. I'm never gonna touch Fahrenheit in this class, so we'll be good. However, to go between Kelvin and Celsius, we have a handy formula. Your Kelvin temperature is just your degrees Celsius temperature plus 273.15. This is something you'll probably want to write down on an index card or something. But it's how we're going to be able to convert between the two. What's interesting is that Kelvin is an absolute scale. Whereas Celsius is a relative scale. What absolute scale means is that there is no negative. Whereas a relative scale can be negative. And so we're going to see that, an absolute temperature is going to be the one we're going to be using when we deal with gases, for example. But the relative temperature is kind of more, familiar to us. That's kind of the ones we're used to saying, it's whatever below zero, that's technically a negative. That's going to be a relative scale. We say that for Fahrenheit, of course, as well. But what's important to note there is that if you have, say, something going from 0 degrees Celsius to 10 degrees Celsius. Actually, let's change that. How about 10 to 20? Yeah, we'll do that. You cannot say that this is double the temperature. Absolutely not. Because it's relative. Unfortunately, so if you go from 0 to 10, you can't say you're doubling the temperature. You're infinitying timesing that temperature, right? I mean, there's no way to go from 0 to 10 in terms of multiplication. And of course, you can't go from negative 10 to positive 10 and say, instead of, doubling the temperature or whatever, I've negatived the temperature. It doesn't work. However, for Kelvin, you can say that. You can say 100 Kelvin to 200 Kelvin is double the temperature. So absolutely we can say that with an absolute scale. Notice also that Kelvin does not take a degree symbol because it is an absolute scale. And looking at this kind of temperature a little bit more, just to throw out one more thing, 0 Kelvin is called absolute zero. And that is the lowest possible temperature. And at which atoms stop moving. completely. So remember we talked about solids kind of just vibrating in place? They do that all the way down until you reach absolute zero. At absolute zero, nothing moves. It's kind of a theoretical limit. We have never gotten to absolute zero. We've gotten pretty close to it, but we haven't actually reached it. And, that's kind of a something that, people take advantage of in, sci-fi and stuff as a result. But that's kind of a fun little fact for you right there. So there we have it. So we can't go to a absolute zero. All right, let me just scroll back up a little bit here. Actually, let's not. Let's talk for a minute. We'll have story time. So the Celsius scale is based on water. Fun little facts here for Celsius. It is based on 0 degrees Celsius is when water freezes. That is what it is defined as. And then 100 degrees Celsius is water boiling. Both of these are kind of at standard atmospheric conditions and blah, blah, blah. We're going to see that we can mess with these given different things, but let's not worry about that. So that's what Celsius is based on. Fahrenheit is an interesting story. The way I remember learning about Fahrenheit was that these numbers, 0 and 100 Fahrenheit, are based on the weather extremes in some guy's town. Somewhere in Europe, right? Wherever Fahrenheit originated from. Where 0 Fahrenheit was the coldest it would get, and 100 Fahrenheit was the hottest it would get. And so there you go. There's your new temperature scale. It was just very convenient for them. And so it's kind of this, technically both of the scales are arbitrary, but at least, the Celsius one is something that you can do all over the world, and it is reproducible. Whereas, just basing it, I feel like, this is the coldest it is, it's 0. It's somewhat arbitrary to just throw that out there. So, yeah. There's your fun story time. So that's where these scales have originated. Typically, most temperature scales have the higher number being the hotter one, the more kinetic energy, but there is a temperature scale that actually has the lower number being the hotter one. I don't know why it exists, but there are other scales out there that are a little bit more niche, let's say. They have their own kind of special uses, or people are just crazy and want to use them anyway. So, all right. That's our temperature tangent for the day. So, let's go ahead and deal with some of these units by talking about metric prefixes. These are kind of used to, alongside scientific notation, these are kind of tools to make really big or really small numbers more manageable. Let me just write that out. Make big, small quantities manageable. So, for example, something really small, you might say it's a microgram. Or a large mass, you might say it's a megagram, or a metric ton. Technically, this would be 10 to the minus 6 grams, and this would be 10 to the positive 6 grams. So we can either use scientific notation, or we can kind of use these units, but it's typically easier to just change your unit up than it is to, mess with the scientific notation. Either one will work, but we're going to see that, it's pretty often that you'd use either one. So they're somewhat interchangeable in their utility there. So, it's just ways for us to kind of describe quantities being similar. So let's go ahead and take a look at what these are going to be. So there is a chart in Discord for you that has all of these, but let's go ahead and go down the list here. So we have giga, mega, kilo, you've got hecta, oops, and then what the heck is next? Deca, yeah. These are going to be our ones that are above the base unit. So whatever our base unit happens to be. We're going to see that these prefixes are going to be useful because they're going to mean the same thing no matter what unit or quantity we're talking about. We're going to see that giga means 10 to the 9th, mega is 10 to the 6th, kilo is 10 to the 3rd, hecta is 10 to the 2nd, and deca is 10 to the 1st power. And so we're going to see that these are going to be useful for us in describing big quantities. So all of these 5 prefixes will talk about big quantities. So we could talk about gigagrams being 10 to the 9th grams, or megagrams being 10 to the 6th grams, for example. We're going to see that it's always going to be one of your prefix thing, which will be equal to whatever this exponent is times your base unit. So, for example, if we are looking at, because at that point we don't really see the use of having a 10 to the 4 or a 10 to the 5. Like, it just kind of is like whatever. At that point, you would just say 10 kilograms instead of some special other unit. As far as I know, those don't exist. We only kind of make it closer to just base unit. We have special ones there, and then we just start going by threes. And that's kind of the way Western counting system works anyway. Yeah. It's the same like with English language, right? We have 10, we have 100, we have 1,000, but then we start combining them, right? We say we have 10,000 or 100,000. We don't actually have another number or another word for 10,000. We just combine them. But in other languages, interesting enough, Asian languages tend to do base 4. So that they, or not base 4, but after kilo, they have another one, basically, where they have a 10,000, they have a word for that. And they actually, instead of then doing it by powers of 3, they would use powers of 4 instead. So this is just, I guess, Western things taking over, and yeah, that's kind of how it worked. So whatever this would be, it could be meters. We would see that, for example, 1 gigameter is 10 to the 9th meters. Or 1 megagram equals 1 or 10 to the 6th grams. Or 1 kilojoule is 10 to the 3rd joules. That's where these come from. Let me put the abbreviations here. Capital G, capital M, K, H, and DK. Deca is not very commonly used, and neither is hecta, to be honest. Most people, when we're talking about the big ones, just go kilo, mega, giga, tera, maybe. No one really talks about hecta and deca, but we'll throw them out there anyways. Cool. Here, we'll do a couple of examples. How about 1 hecta? What unit shall we have here? Hectawatt. Why not? Is 100 watts. And 1 decaliter is 10 to the 1 liters. I don't know. It's bizarre to see hecta and deca in use, at least for me. So the beauty of all these is they can use for any unit. So for example, we have units of length, mass, energy, power, and volume here. So you can use it with whatever you like. Alrighty, going down now, if we want to look at things that get smaller, we're going to have one for 10 to the negative 1, 10 to the negative 2, 10 to the negative 3, just like before. And then we start going by threes again. Again, that's just kind of the convention there. And the words that we're going to have for these, we're going to have deci, centi, milli, micro, nano, and pico. These are going to be our prefixes here that we're going to be using. And whatever they happen to be, they would be equal to those powers of 10 times your base unit. If we look at deci, that is... oh my gosh, is deci just D or DC? I think it's just D. I don't even remember because I don't ever use this unit. Let's find out. Let's check Discord because I've forgotten about deci. It is just D. Oh, and deca is DA. Go figure. Go figure. Who cares? Centi is C, milli, micro, nano, and pico. Thankfully, these are all kind of nice. The one that's special here is micro. Micro is the Greek letter mu. It is kind of it looks like a U with a long kind of thing to start with. So that's the only one that's a Greek letter. The rest are all kind of regular ones. Here I'll fix deca. Apparently that one I'm using the German one instead of the what was it, DC or DE? I don't even remember. Who cares about deca? We don't care. Let's use some examples. It is DA. Okay, go figure. Aha, now it's fixed. So something like deci, you could say, 1 deciliter is 10 to the minus 1 liters. Or a 1 centimeter is 10 to the minus 2 meters. For milli, why not? Let's use grams. 1 microamp is 10 to the minus 6 amps. The point here is that the prefix, or the little kind of subunit here, is going to be what tells us the exponent value. It's telling us the magnitude of how something is. 1 nano. Let's see. How about what unit haven't we used yet? Nano ohm. Random units here. And how about pico? Picosecond. Why not? 10 to the minus 12 seconds. So we have all sorts of fun use here. So these ones we typically will actually use the small ones. So like centi is actually something that's used fairly frequently. Deci is used in certain medical contexts, like they'll report glucose in milligrams per deciliter. Not sure why, but that's something that's commonly used. But kind of the big ones that we're going to see the most often will be milli, micro, nano. Those are going to be the biggest ones for us in chemistry. So we will see pico sometimes. But yeah, those are kind of the ones we're going to be using. So we're going to end up having all of these kind of factors here that we can use to convert things in between. For example, if I have something that is 1,267 centimeters, we could find out how many meters that is. And we're going to be using a process called dimensional analysis. Dimensional analysis, aka unit conversion, to work this out. Essentially, we're just using a bunch of different proportions or equalities that we know that we can basically apply to convert the units of something. So if I were to take, for example, here's an impressive fact for you. If I multiply this, let's say, by 8 over 8, nothing changes, right? I'm allowed to do that. You're allowed to multiply something by 1, and it's not going to change it, right? We're going to see that this works. This works because 8 is equal to 8. This is nothing amazing, right? Because 8 is the same thing as itself, we're multiplying by 1. When we multiply by 1, nothing changes, right? So we're going to see that whenever we have an equality between units, we can use them as a conversion factor. So if I tell you that 1 centimeter equals 10 to the negative 2 meters, there it is, we can use this. Just like how 8 is equal to 8, if we multiply something by a centimeter and 10 to the negative 2 meters, it's the same thing as multiplying by 1. We're not changing anything, so we're allowed to do it. So we end up getting kind of two things from this. We could either use this as 1 centimeter over 10 to the negative 2 meters. That's the same thing as 1 over 1 or 8 over 8, because they're the same as each other. We've already displayed that those two are equal to each other. Or we could have 10 to the negative 2 meters over 1 centimeter. Again, 8 over 8. Doesn't matter which one I put on the numerator or denominator because they are equal to each other. So I can flip it whichever way that I find useful. So let's go ahead and take our original number, that 1,267 centimeters, and let's try multiplying it by one of these fractions. We can choose either one. Let's choose the first one. Why not? Let's do that. Let's try this out. Because these are equal again, we're allowed to do this. We're allowed to multiply them. If we do that, we get some bizarre unit combination that doesn't quite make sense. So maybe that wasn't the best idea. However, we can take advantage of our knowledge of how units work and how multiplication division work if we actually use that other conversion factor, the second one instead. Oh, look what's going to happen now. We're going to see that our units of centimeters are going to cancel out. Right? Anything divided by itself will cancel out, right? That's how division works. And so note that we are now left with the units of meters when we do this. We ended up canceling out our centimeters. We're going to end up with the unit that we want, which was meters. So doing this, we're going to get 12.67 meters. I'm just multiplying them across there. And that would be our happy answer for seeing how many meters that centimeter thing was equivalent to. So does this kind of make sense? You're going to want to arrange your conversion factor so that the units you don't want will cancel out. And so remember, we have that luxury because they're equal to each other. So we can put whichever one on the numerator, whichever one on the denominator that we want to get canceled out. All right. Any questions on that one? Alrighty. How about if we go from... Okay, yeah, what's up, Cassie? Or, I don't know if that was a yes to I have a question or yes to is that all good? If you have a question, just throw it out. In the meantime, I'll keep on looking at. Why do we always finish the equation? Yes. Not quite sure what you mean by finishing it. You can do either one. Doesn't matter. If you want, you could have put this in scientific notation if you really wanted. It really doesn't matter to me. Unless something is bigger than like 10,000. So if it's really big, I would throw it in scientific notation. Or if it's really small, throw it in scientific notation. But for us, those two numbers, there's really no difference. I'd be happy either way. Technically you could leave it as 1267 times 10 to the negative 2, but that's a little strange. So either put it in proper scientific notation or go ahead and put the number out. So don't put it where it's just like some random exponent. So either scientific notation or standard notation would work, but let's just for now, here, let me just move this out of the way. Let's avoid doing it like this. Like that's a bit bizarre for me. So either one of these would be okay. Happy, angry. Okay, so hopefully that will answer that. Cool. Okay, so if we were to do the kilometer one, big time one is absolutely right. I think it's Edward, right? Or Ed, whichever one I don't remember. Or Ted, I don't remember. I'll remember one day. All right, let's go ahead and convert this to kilometers. So, indeed we Eddie. Okay, so I wasn't right with any of them. Go figure. So, with this one, what I like to do when teaching this is to first come up with a plan. Is there a way we can go from centimeters to kilometers? What kind of steps are we going to need here? When we're going through these kind of metric prefixes, it's a good idea to kind of use the base unit as your kind of like middle ground. So what I would do is I would first go to meters and then go to kilometers. You're welcome to go directly if you want to make your own conversion factor. If you like doing that, go right ahead. You're welcome to do that. It'll work. But I like to be kind of methodical about it and always go through the base unit. That way we're going to not have any kind of mistakes. So we're going to in fact need two conversion factors here that we're going to deal with. One from centimeters to meters and the other from meters to kilometers. So we've already looked at that first one. We saw that 1 centimeter is 10 to the minus 2 meters. And if we look up on that table, we're going to see that 1 kilometer is 10 to the 3 meters. The way that I've given you that table, it's telling you that one of your prefix unit will equal the exponent times the base unit. That's the way I like to do it. People have learned this, probably different ways. Some people will say 100 centimeters equals 1 meter. That's fine. It works. You're great. Or you can say 1 kilometer equals 1,000 meters. It all works. Do what you like. Just make sure that you're not mixing things up. So I will always be doing it this way, where I have your prefix unit with 1, and I will have your exponent unit with the base. So let's go ahead and see how this works. So remember that when we have these conversion factors, we're going to use them as fractions. because they are equivalent to each other. And since we already know we're going to be using 2 conversion factors, we can do that. So, just like before, we're going to want to arrange our first one so that we have centimeters canceling out. So we should put centimeters, therefore, on the bottom, on the denominator, so that it cancels out with the centimeters before. And so as a result, we're going to put the other part of that equality on the top in the numerator. All right, hopefully so far so good. With the next one, you can see that we have now meters in the numerator that we need to get rid of, because we don't want actual meters in our answer. We only want kilometers. That's what the problem is asking us to do. So we're going to want to put the meters portion of that equality on the denominator and the kilometer portion in the numerator. And we should always double check that our units are going to cancel out. Indeed, centimeters cancels, meters cancels, we're left with kilometers. And so all we have to do now is the math. So we would multiply 1267 times 10 to the negative 2, divided by 10 to the third, and we would get, I guess, let's see, that'll be 10 to the negative fifth. So that'll be 1.267 times 10 to the negative 2, if I can do that in my head properly. Or, of course, you could say 0.01267 kilometers. Either of those would work out. Someone double check for me. Always a good idea. I try to do things in my head when I can, but sometimes that backfires. As we know, I couldn't even do that simple subtraction earlier, so or yesterday. So always do this as well. It's good practice anyway to just get familiar with whatever you're using as your calculator. So good idea to do that. So hopefully this is the answer that we get. All right. Hopefully that's okay. So with all these prefixes, it will definitely benefit you to memorize them. I don't really have a means of kind of forcing that on you because it is online this semester, so it's kind of up to you. I mean, yes, you're welcome to just throw a chart up there, and there you go. You've got it for reference. But you're going to see that we use this stuff quite a bit. And so it'll be definitely beneficial for you to kind of memorize it. Let's do another one. What unit shall we want this time? How about we do... how about megagrams? All right, so I've got 6.25 times 10 to the 8th micrograms of whatever, and I want to find out how many megagrams that is. So just like before, it's probably a good idea to go to the base unit in between, which would be grams. That's going to be our base unit. So because we have 2 conversions, we're going to need 2 conversion factors. First one's micrograms to grams. If we look up on our chart, we see that 1 microgram is 10 to the negative 6th grams, and 1 megagram is 10 to the positive 6 grams. All right. And so we're going to do much the same process here. We would start with our measured quantity. And now we're going to use our 2 conversion factors to get our answer. So we have 2 things to put in here. First one we should do is probably something with micrograms, so we can get rid of those micrograms. Alrighty, and looking at that, it looks like we do have conversion factor number 1 that has micrograms. So let's go ahead and put our micrograms in the denominator so that they'll cancel out. And our grams up there. Oop, yeah, that's right. And then if we want to cancel out the grams with our next one, that one's going to go in the denominator. We'll have megagrams on top. And look, I don't even need a calculator for this one. I say that, right? 6.25 times 10 to the negative 4 megagrams. Hooray. Let's double check, by the way, that our units have canceled out. Yep, we have micrograms canceling. We have grams canceling. We're left with megagrams, which was what we were looking for. Thankfully for us, the numbers don't change. We just are changing our exponent. And so makes it easy, right? Alrighty, let's do another one. How about we do this? How about we do let's do something with Hertz. Hertz is a frequency. It's per second, where we have seconds to the negative 1 power. That means it's over seconds. We have 82.4, whatever it is, per second. This is something that would be, like beats per minute or revolutions per minute if you're looking at like something like that. So this is whatever per second. So 82.4 things are happening every second, whatever this is. Let's see what that is in per minutes. Let's see what that's going to be. So we're going from whatever this is per second, cycles per second, to cycles per minute. Let's look at that one. We know, of course, that we have a conversion factor between seconds and minutes, right? Hopefully, we all know that 60 seconds is 1 minute. Let me just erase this. We're going to put it down here. Let's see how this one works. I'm going to just put the seconds on the denominator, because that's what the same thing as having that negative exponent is. Notice here, because the unit that we're getting rid of is in the denominator, we're going to have to put 60 seconds on the top, so that the seconds will cancel out. Does that all make sense? So because our unit is in the denominator, we need to put our conversion one in the numerator so that they cancel out. Just like before, if we had it in the numerator, we want to put it in the denominator to get rid of it. This time we just have the opposite case. And of course, we're going to put 1 minute then on the other side. And so we're going to end up getting the answer of 82.4 times 60. Yes, exactly. So seconds to the negative 1 power. Remember that, like, for example, 10 to the negative 3rd power is the same as 1 over 10 to the 3rd. Negative exponents just mean it goes in the denominator. Yeah. One thing to note about Sig Figs here, thankfully for most conversion factors, we do not think about their Sig Figs. We'll talk about this on Monday, but those are called exact numbers, and exact numbers will not mess with our Sig Figs. So technically this one we should round to 3 Sig Figs because our 82.4 was in 3 Sig Figs. So we should round this number to 49.40 per minutes, whatever those happen to be. Beats per minute. We're going really, really fast. Or revolutions per minute in our car. So we would still want to apply our Sig Figs here. So yeah. Alrighty, so we're out of time. There is a worksheet on this. It is not due this weekend because we still have some more things to talk about with this. So right now we just have the lab sims and then your Sig Fig worksheet that'll be due on Sunday. So make sure you get those in. Your other worksheet you can start working on, but it's not due yet. All right. So with that, I guess I'll see you on Monday. If you have questions, throw them in Discord. It's already great to see you guys are helping each other there. I'm happy to help out as well. So, yeah, will be great. Okay, see ya.